Alrighty, you guys. So today we're going to be covering a problem that wants us to calculate the kinetic energy of air going through a pipe. So we're told that we have air going into this pipe that has an inner diameter of 7 centimeters. And the temperature of the air going inside this pipe is 300 degrees Celsius and at a pressure of 130 kilopascals. Now, how fast is this air traveling? Well, that's given to us too, and that's 42 meters per second. So how do we even approach this? Well, let's write down what the information we're given. Let's draw our little diagram, and then I'll show you how to approach the problem. So, given, we're told that the temperature is 300 degrees Celsius, right? We're also told that the pressure is 130 kilopascals. And we're also told that our velocity, which is noted by mu, equals 42.0 meters per second. All right, now these are the properties of the air going into our little tube, our little pipe. All right, so our little pipe, now I'm not going to make any corny jokes about drawings. You know, we've all heard them all. Oh, I'm not an artist. So air goes in, air goes out. Properties are for this input stream, right? And then this is out, our output stream. So, what's next? Well, we drew our diagram, we have our air. So, the easiest way you want to approach this problem is finding the mass flow rate. Hopefully you know what mass flow rate is. If you don't, it's the amount of mass moving over time. So, that's usually depicted by m dot. Okay? So, how do we set this up? Well, we grab our velocity given here. We have 42.0 meters per second. Okay, you know what? I want to make it easier for you. Let's move this crap out of the way. We have 42 meters per second. Write it like this because you'll see why. You'll see why. And then we're going to multiply that by the area of a circle because it's going into our pipe, and you know, pipe's a circle. But what's the area of a circle? Well, I don't know. Pi d squared over 4. There's another variation, pi r squared or something. I don't know. Google it. But this is one version, pi d squared over 4. So you write pi, right? And you multiply it times your diameter. Well, what's our diameter? We're told that our diameter is 7 centimeters. Now here's a pro tip. If you're given a measurement and it's like centi, deci, kilo, whatever, try to convert it to the base unit. Get rid of the centi, get rid of the kilo, get rid of the extra stuff. You don't want it. You want the good stuff, the meters, right? So what's centi? Deci, centi, that's 10 to the negative 2. So it's 7 times 10 to the negative 2 meter. And now that's just something you have to memorize. If you don't have that memorized, just Google it. So 7 times 10 to the negative 2 meters, right? And then square it, because we said it's squared. And then you divide that whole thing by 4. Okie doke. Good. So now we want to get rid of the meters. We want it in liters. So what do we do? How do we do that? Well, 1 meter cubed. And then at the top is 10 to the third liters. That's equivalent. That's not given to you. It's just something you're going to have to know. There's some special rules with, regarding density of water and all that. But for this problem, just know that 1 meter cubed is equivalent to 10 to the third liters. Okay? Now, we're also told in the problem statement that the gas or the air going into our pipe is behaving as an ideal gas. It has ideal gas behavior. As a result, we have to use, STP stuff. And if you don't know what the standard temperature, pressure stuff is, I'll make a video, if I haven't uploaded it yet already, that explains in detail what that is and how you apply it to these kinds of problems. But basically, at the gist of it is, we use like a reference point. We say things are to be referenced at 760 millimeters of mercury or 1 atmosphere, things of that nature. It's beyond the scope of this video, but check this out. I'll show you how to solve it. So, since we're told that it's behaving as an ideal gas, we have to use these middle conversion factors. So, at the top, we're going to put 273 Kelvin. And hold on, I'll explain it in a bit. And then at the bottom, we put 300 degrees Celsius, the one we're given, plus 273. Why 273? Because if you add 273 to Celsius, you get Kelvin. Okay? So now, this Kelvin right here is at STP. That's why I'm putting it at the top. And we want Celsius to Kelvin. That's why we added 273 down here. Okay? Remember, we're doing this because it's at STP. So here we have another one. Now we gotta convert the pressure we're given to STP, whatever. So 101.3 kPa, not given to you, but it's at STP. If you think of STP, 101.3 kPa. Okay, and then at the top goes your 130 kPa as well, and that's the one that you are given. Cool. Just a little pro tip: 101.3 kPa is the equivalent of 1 atmosphere. Let me make this a little smaller because I don't want to go over the page.
There we go. Alrighty.
So then we have our pressure here, right? And we took into account temperature, pressure. Now we need liters. So at STP, associate 22.4 liters. And then you could write in little parentheses STP. It's a little thing they tend to do in textbooks. And at the top, it's 1 mole. Whenever you have 1 mole at 1 mole at STP, it's going to be 22.4 liters STP. Okay? And then finally, we put the molar mass of air. And if you Google that, it's 29 grams per 1 mole of air. Okay? Great. We have a whole bunch of random crap on our screen. What does it mean? What is it going to help us with? What do we do next? Well, check this out. So the end goal here is we want to get mass over time, right? And the easiest way to approach this specific problem is converting the data we're given to grams over second. Following this specific map will give us that result, right? Now, if you were to do a different problem, you might want I don't know, kilograms per second or pounds per second, something crazy. I don't know. We got to cancel some of these units out, right? We have m cubed here, and then we have an m here, but that one's squared, and we have an m here. Therefore, we have 3 m's at the top, right? And then we can cancel out this m cubed. We have liter here. We have liter here. And this goes with the STP. Kelvin, Kelvin, kPa, kPa, mole, mole. And that is it. Great. Oh, would you look at that? We have grams. We have seconds. Perfect. Perfect. So we plug this into our calculator, and the final number we get is 127.946 grams per second. Okay? Good. So what do we do with this number? What does it mean? Well, this number is our mass flow rate. Now, if you remember from physics, there's the velocity formula for kinetic energy, and that is kinetic energy equals 1/2 mv squared. If you don't remember it, well, there you go, 1/2 mv squared. For us, for fluids, stoichiometry or whatever, very similar thing, but since we have air, we have gases, we put a dot symbolizing there's a time aspect to it because it's moving. 1/2 m because mass flow rate, and then instead of a v, we typically use a u, but it's the same thing. It's not gonna affect your answer at the end. Mu squared, and that's our little u that was given to us earlier here in the problem, and then the mass flow rate is the one we just solved. So good stuff so far. Let's see what we got next. So we start plugging things in. 1/2 m, and then our mass flow rate 127.946 grams per second. Great. And then our u, we're told that u is 42.0 meters per second, right? Oh, don't forget the squared. Cool. Now, normally you would simplify this. You make that m squared, second squared, and then 42 squared. You can simplify it, get a constant, whatever. But before I do that, I'm going to elaborate this a little bit further, and it's going to make it a much cleaner solution, and you'll see why. So pretend I simplified this, right? And you'll get a specific answer. It doesn't change if I just rewrite it. It's just expanded form, if you will. But let's say, this is our simplified version. Meters per second squared, right?
I didn't quite catch that.
Oh, not you, Siri.
Please repeat it.
Alrighty. So what do we do next? Well, check this out. It's gonna get a little crazy, but you'll manage. So we have 42 meters per second squared. This is our KE formula, etc. I'm gonna convert this grams to kilograms. I'm gonna do that. We know that 1 kilogram is 1,000 grams, and if you didn't know that, you now do. So grams cancels out, and we have kilograms, right? But I'm not gonna stop there. If we look up a table of unit conversion factors, we're gonna find that 1 Newton is equivalent to 1 kilogram meters over second squared. If I look up another unit, I'm going to find that, oops, just kidding, not that one. I'm going to find that 1 joule is equivalent to 1 Newton meter, okay? And I'm going to find another one, and I'm going to find that 1 joule is equivalent to 1 watt, okay? Okay. So, what do we do with this information? Well, let me show you. I'm going to multiply this by 1 Newton, right? And I'm going to use this one right here. We say 1 Newton is equivalent to 1 full of these. So I'm going to put 1 kilogram meter times meter, right? And we have a second squared. Normally we could write it at the bottom here, but I'm going to clean it up a little. I'm going to multiply it times second squared. And I'll show you how that works right now if you don't understand how I did that. And then I'm going to multiply this by the this unit conversion factor. 1 joule over 1 Newton meter. Now, you're probably wondering, what did I just do here? Well, check this out. We said 1 Newton is equivalent to 1 kilogram times meter over second squared, right? Which is this 1 kilogram meter over second squared. That's a terrible looking name, but just bear with me. And what this is equivalent to, if I multiply the reciprocal, and this is just algebra. If you don't get this part, then I'm sorry, guys. And let's make me some more room. And then you multiply what you do to one side, you do to the other, second squared, kgm. Okay, so these cancel out, cancels out. But oh, what do you see here? 1 Newton times second, cool. And at the bottom, kilograms times meter. Perfect. It is valid. I didn't make it up. So I'm gonna delete this. That makes sense. And let's get back to the problem. Alrighty. So we're gonna simplify this again. We're gonna get rid of the units. We're gonna get rid of any unnecessary nonsense and simplify the answer. So before I continue, you're probably wondering, why did I just do what I just did? Well, we're gonna multiply kinetic energy times some unit conversion factors, because if we stopped here at the kinetic energy, we would gotten different values. We would gotten newtons times joules or something, but we want watts, and to get watts, we have to play with the unit conversion factors. So it's not like we're multiplying them by some other random, part of the problem that wasn't given to us. It's just messing with the unit conversions, with the units to get the answer we want. So let me show you. We have second squared here, and then we have seconds here at the bottom. Grams, that one looks easy to cancel out. Cancel that out. We have kilograms. Oh, great. We have kilograms here. Second squared. Get rid of that. And then we have meters squared. And at the end of it, oh, look, Newton. And then we have Newton there. And it looks like we're left with joules over second. But wait, what does that mean? Joules over second. Oh, this is what that means. That 1 joule over second equals 1 watt. Sorry. But that's what it's supposed to mean. 1 joule over second equals 1 watt. Great. Alrighty. So we plug this into our calculator, and the final answer we get is 112.848. I don't know what happened there, but that's an 8. And then joules over second. But wait, we know 1 joule over second equals 1 watt. Therefore, we could say 848 watts. What is going on? Watts. Cool. So we have our final answer. But now let's say we're told we got to find it at 400 degrees, right? And we want to take the difference of watts at 400 degrees and 300 degrees. So now we got to find the velocity of the air at 400 degrees, and we already know the watts at 300 degrees. So we used the new velocity at 400 degrees to find the watts at 400 degrees. A little redundant, but it's valid. So how do we do that? Okay. Well, why are we finding a new velocity? Why are we doing that in the first place? Well, notice that mass does not change. Okay? Only the temperature. And that would be at 400 degrees. And because we're changing the temperature, we're increasing the amount of mass going through the pipe. And because we're changing the temperature, we're only changing how fast that air is traveling, but not the total amount of air traveling, right? The mass remains constant. So if we look up here, we found that this is how much is traveling through our pipe, right? With the given information. So we're going to bring that down here again. 127,946 grams per second, right? Right. And then we're going to multiply that by our molar mass of air, 29 grams. Put that at the bottom. And you'll see why I'm multiplying it by these specific unit factors. Remember, there's no real critical analysis to this. It's just a matter of playing around with the units, trying to get the final result, which is some sort of component that's going to give us length over time, our velocity, if you will. So it's at STP, right? Remember? Oh yeah, you remember. 400 plus 273, and that's Kelvin, right? Yes. And then 273 at the bottom, because it says STP. And then you do the same thing with this side, 101 kPa. Something goes there. And then at the bottom, you got 130 kPa. Okay? And then you multiply it again. Remember, liters, 22.4. STP liters. And then 10 to the third cube for liters at the bottom. And then our area of a circle. So we just write the inverse here, pi. And then it's equivalent to 0.07. Or if you want to write the other longer way, that's fine too. And you will not all, but the only ones you should get left at the end is 49.32 meters per second. Okay? So cool. We have our new velocity for our 400 degrees temperature. So how do we use that to find our watts? Well, very similar to what we did up here. They gave us a velocity, right? And we were able to find the amount of energy. Well, check this out. We have a new velocity. We repeat the same thing we did up here, and we find our new energy answer. So Ke equals 1/2, right? And that's mu squared, right? And then we know 127.946 grams over second, right? And then we multiply that by 49.32 meters per second. And that's squared because it's velocity. And then we're going to throw a kilogram there, and we're going to divide it by 1,000 grams because they're equivalent. And then, again, the whole 1 Newton times second squared over kilograms over meter, as I proved it above. And then finally, we get to 1 joule, and then we have Newton meter. Okay? Sloppy M's. Simplify that into your calculator. You got 155.8 joules per second. Cool. So now what? Well, rewrite it. Why not? Boom. Great. Now we do this. We write a fancy triangle so it looks like we know what we're doing. Just kidding, we do. Delta KE equals, and then 400 degrees Celsius wattage minus 300 degrees Celsius wattage, right? So that's going to be 155.8. Wow. So that's going to be 155.8 minus 112.848. And that's going to be watts. We simplify that, and we have 42.952 watts. And that is it. That's how you solve that problem. So as you can see, there's no real analysis you got to do. There's no real well, there is some thinking. It's just a matter of playing with the puzzle pieces that you're given. But with enough practice, you have a general idea of like, maybe I should try using this unit conversion factor over this one, because I want to get mass over time to find my wattage, and having mass over time, that's going to allow me to get wattage or joules over second or whatever. It's doable. If you have any questions, leave them in the comments below. I'd love to read your comments. I'll be making a series of these, more exercises. It can be very long and tedious problems, but with enough practice, you'll be able to solve them. So, I'll see you next time. Take care.